Hi, my name is Gilad Ashrov from Bar-Ilan University, and I'm going to talk about our paper, Simple School, Graded Dispersal and its Applications for Byzantine Fault Tolerance. This is a joint work with Itai Abraham and Anirudh Chandramouli. In this paper, we focus on several different applications for Byzantine fault tolerance, like in synchrony, gradecast, multi-value Byzantine agreement, or broadcast, and in asynchrony, reliable broadcast. In this talk, I'm going to focus only on the application of broadcast. So what is broadcast? The goal is implementing broadcast over point-to-point channels. In a broadcast, we have a distinguished party, a sender, that holds a message M, and we assume that the message is of size L bits. The goal is that all parties will receive this message. There are two properties that have to be satisfied. Agreement, all honest parties must output the same message, and validity, which means that if the sender is honest, then the output of all parties must be the input of that honest party, honest sender. This should hold even if some parties are corrupted, the sender might send different messages to different parties might report different messages to different parties, and so on. Now, the settings that we are going to consider are the perfect setting, which mean that we assume that the adversary is computationally unbounded, there is zero probability of error, and in that settings, it is known that broadcast, the number of corrupted parties must be at most 1/3 of the participants. So what is the optimal broadcast in this case? Well, if the sender wishes to broadcast a message of size L, then the best we can opt for is NL total communication. This is because if each party has to receive L bits and we have N parties, so overall, the number of bits being transmitted is at least N times L. Moreover, we can hope to achieve a constant number of rounds. However, there are two lower bounds, two known lower bounds. One about communication, which says that broadcasting 1 bit requires at least N² communication. And one for rounds, which means that any deterministic protocol, there must exist an execution that requires at least T+1 rounds. And RT, just as a reminder, is something like N/3. So what we get is that the best one can opt for broadcast is broadcast with Ln plus N² communication and order N rounds if we have a deterministic protocol, or expected constant number of rounds if we have a probabilistic protocol, but we can never really achieve a protocol that finishes in a strict constant number of rounds or any little o of N number of rounds. So the best we can opt for is as we have here and what exists in the literature. So previous works improved the communication of broadcast over the years, starting with N²L of Berman, Garay, and Perry. The latest is NL plus N³ log N by Nayak et al. All of those are with order N rounds. And very recently, an interesting work by Chen shows a broadcast protocol that is almost optimal. It achieves NL plus N² log N communication in order N rounds, and which is only log N factor away from being optimal. Chen called this protocol as COOL, coded, which stands for Coded Byzantine Agreement Protocol. Unfortunately, the analysis of COOL is complex and lengthy. In our work, we provide a simpler analysis, which takes roughly a page and a half. As part of our work, we show that the core of COOL is essentially a new variant of dispersal, which we call graded dispersal. Defining this graded dispersal variant allows us to distill the novelty of COOL's protocol consistency check and build applications that are based on COOL in a more modular way. Our simpler analysis also allows us to improve the protocol by reducing the number of rounds and improving the communication by 40%. We then show applications. We show how to utilize graded dispersal to implement gradecast. Our protocol improves the state-of-the-art in gradecast needing only for 5 rounds, whereas the best previous required 8 rounds. This is thanks to our tighter analysis. Moreover, we show how to utilize greater dispersal to implement Byzantine agreement and broadcast, wherein all those primitives reduce the communication by 40%. We also show a variant of greater dispersal in asynchronous networks, and our protocol has 40% better communication than best prior, and also reduce the number of rounds from 9 to 8. Again, this is all with perfect security, and reducing the number of rounds as it's practically important. Let's start with the definition of graded dispersal primitive. So in this primitive, the input of each party is some polynomial of degree d, and the parties wish to find out whether they hold the same polynomial or not. Now, they're not going to really reach full agreement. Instead, they're going to output some grade, where grade between 0, 1, or 2, where 2 is like, I'm confident that there are enough parties with the same input. 1, I'm not so sure, and 0, I don't know if my input is like the others. Now, we require the following properties. First of all, validity. If all honest parties start with the same input, then they all gonna have grade 2. On the other hand, we also require weak graded agreement, which means that if some honest party has output 2, grade 2, then there are enough honest parties with grade at least 1, and all those parties that have grade that is non-zero must have also the same input as the party that outputs grade 2. So if we have one honest party with grade 2, there are at least t plus 1 honest parties that have grade at least 1, and they must hold the same input as the party that outputs grade 2. On the other hand, all the honest parties that have different inputs, they must have grade 0. So let's go over the graded dispersal protocol. As an input, each party holds a polynomial of degree d, and as we mentioned, the goal is to understand whether the parties hold the same polynomials. Instead of sending the polynomials to one another, which is a lot of communication, in the first round, every PI is going to send to every PJ just 2 points on the polynomial. Its own point, fi of I, and it's the other party's point, fi of j. The parties then see if the messages they received agree with their inputs. Each party generates a list of all parties that actually agree with its own polynomial. If the list is large enough, at least n minus t, then that party is going to send OK1 to all other parties. The parties then see what the OK1 messages they received and remove from their agree set all the parties that disagree with them, that they did not receive, all the parties that did not receive OK1 message from. If this agree set is still large enough, it's still of n minus t, then they're going to send OK2 to everyone. At this point, we already know what the output is going to be. If a party sends OK2, and it received at least 2t plus 1 OK2s, then it's going to output grade 2. It's confident that there are enough parties with the same input and agree with his own input. If a party sends OK2 but received at most 2t OK2s, then that party outputs grade 1. And otherwise, if it did not send OK2, it just outputs grade 0. Now, before we actually start the analysis, we want to remark 2 differences from the COOL protocol. First, our title analysis allows us to work with polynomials of degree t over 3 instead of t over 5. Looking ahead, when we want to agree on larger messages, we'll have to break them into blocks, into polynomials, and the fact that we can accommodate larger polynomials allows us to reduce the communication by 40%. Moreover, we remark that in the original COOL protocol, there is one more round of OK messages. We show that this additional round is unnecessary. In fact, it just just makes the analysis more complicated because there are more cases to consider. And practically speaking, reducing a round is also important. Okay, so let's go to the validity and see why validity holds. Remember, validity, if all parties start with the same polynomial, all honest parties start with the same polynomial, they are all supposed to have grade 2. So if all honest parties start with the exact same input f of x, they all gonna agree on the messages they exchange. The set of honest party, they're gonna send points that they agree with one another. In the agreement, in my agree set, I'm gonna see all the honest parties. I'm gonna say, okay, 1 to everyone. No one is going to exclude me from their agree set. I'm not going to exclude any other honest party from their agree set. And I'm going to send OK2 to everyone. And so all honest parties send OK2 and receive OK2 from all honest parties. And therefore, we have enough OK2s that we receive, and everyone is going to output grade 2. Now let's look at this weak graded agreement property. The goal again is to show that if someone outputs grade 2, then there are a lot of honest parties that outputs grade at least 1, and they all have the same input. First, we partition the set of honest parties according to their inputs, and I'm using notations and relating to F1 for denoting both a set and a polynomial. That is, F1 is the set of all honest parties that hold the polynomial F1 as input. We now have 3 claims. First, we claim that no 3 honest parties with different inputs can send OK1. Then, we show that if there is a large set of parties with the same input, then only parties from that set might send OK2. This implies that if there is some party with grade 2, there must be enough honest party that send OK2, and those parties must hold the same polynomial. Third, we show that if there is no large set, then no honest parties output grade 2. We start with the first claim. So we are going to show this by a very simple counting argument. Assume there are 3 parties that send OK1 by contradiction. The agree set must be greater than n minus t. Now, exclude from their agree set all the corrupted parties. I'm going to denote this set as SI. So SI is the agree set when I look only at the honest parties in that agree set. We get that all those agree sets, now honest agree sets, are at least of size at least t plus 1. And on the other hand, the intersection of any pair of agree sets is at most d. And this is because every 2 distinct polynomials can agree on only d points. Now, by inclusion-exclusion argument, if we look at the union of all those 3 agree sets, we get that it must be large. It must be larger than 2t plus 3, where here I'm using taking into account the fact that d is the degree is at most t over 3. On the other hand, this set, the union of all agree sets, is no more than the number of honest parties. It's included in the set of all honest parties, which is of size 2t plus 1, and we get here a contradiction. So we get that no 3 honest parties with different inputs can send OK1. We're now showing the second claim. If there is a large set, then only parties from that set can send OK2. Again, this is the counting argument. Specifically, we partition each one of the sets to 2. F1 plus is going to be all the parties in F1, for which the polynomials F1 and F2 agree on that input. So it's all i's in F1 such that F1 of I equals F2 of I. And likewise, I'm going to define F1 minus to be the complement set. So it's all I in F1, for which F1I doesn't equal F2 of I. Now, we claim that parties in F2 minus do not even send OK1. This is because they disagree with all of F1, and they cannot reach any support, cannot receive any support from parties from F1. Now, F1 is really large. It's at least size t plus 1. So I can receive support from at most 2t parties, and I cannot reach 2t plus 1. So my agree set is not big enough, and I'm not going to send OK1. Because those parties in F2 minus do not send OK1, we're going to see that all those parties in F2 plus cannot now send OK2. This is because they can receive support, can receive OK1 only from parties in F1 plus. Specifically, they cannot receive support from F1 minus because they disagree. So I can receive only from those parties, from the union of those two sets and the corrupted parties. But the union of those two sets is at most D, because the two polynomials can agree on only D points, and this is bounded by T over 3. Together with the T corrupted parties, I'm going to receive at most T plus T over 3 points, and I don't have enough to reach 2T plus 1. So I'm not going to send OK2, and we get that all those that send OK1 must be from F1. They all hold the same polynomial. The third claim, we're going to show that if there is no large set, the no honest party outputs grade 2. Again, a counting argument. We claim that parties in F2 minus do not send OK2. This is because parties from other sets do not send OK1. And parties in F2 minus disagree with F1, so can receive support only from F2 and the corrupted parties. However, this is at size at most T. The corrupted parties is again at most T, and we get only 2T agree set, so they're not going to send OK2. The same argument is for F1 minus. They're also not going to send OK2. And we get that the only parties that might send OK2 are from F1 plus or F2 or F2 plus and the corrupted parties. However, those together are not so many parties. There are only D plus T OK2's messages that are going to be sent. And no party is going to receive 2T plus 1 OK2 messages, and therefore no party outputs grade 2. Okay, so we now show how to use graded dispersal to implement broadcast. Assume that the sender has order n bits. If it has larger, we need to break it into blocks. We're going to encode its order n bits as a polynomial. It sends its polynomial to each one of the parties. The parties run the graded dispersal, and then the parties run 1-bit Byzantine agreement to find whether there is a party with grade 2. The Byzantine agreement guarantees that they all agree on the output of the agreement, and so they're all going to agree if there is a party with grade 2. If there is a party with grade 2, then the parties are going to run some data decimation protocol, which is of one round, where they reconstruct a polynomial. We reconstruct the polynomial from the parties that do have the polynomial, or that they have grade at least 1. And so they're going to reconstruct the message of the dealer, and we actually going to have a broadcast. So before I conclude, I want to mention another line of works on broadcast. We mentioned that in any broadcast protocol, there must exist an execution that requires at least T plus 1 rounds. This implies that having a protocol with a strict constant number of rounds, or any little o of n rounds, is impossible to achieve. We mentioned that this leads to a line of work with order n rounds, and this is the one that I focused on this talk. However, there is another line of work originated by Feldman and Micali in 1988 that shows protocols with expected constant number of rounds, where the latest work by myself and Chandramouli achieving order n L plus n cube log square n communication. So essentially, there are two families of protocols for broadcast. Protocols that are efficient in terms of communication, but have many, many rounds, or protocols that have small number of rounds, but have larger communication. And a very interesting open problem is whether there exists a protocol with order NL plus n squared log n communication, or n squared communication, with expected constant number of rounds. So for conclusion, our main novelty is a simple analysis of pool. This offers new insights, and it's easier to utilize Pool now in other applications. We show other applications, and our title analysis also shows how we can reduce rounds and achieve better communication. With that, I want to conclude. Thank you.